So as a seismologist, typically what I tell people outside the lab is that I study earthquakes. The source physics experiment is really to help us understand the difference between earthquakes and explosions and help us be able to monitor them. The goal here is to improve our capabilities to monitor and detect nuclear explosions underground, which is pretty essential for global security, for our nation's security. SPE, or the source physics experiment, it's a series of explosions, underground chemical explosions. So we did 3 phases. The first phase, we took what we call a simple geology, which is granite, and went out to the test site, and we drilled a hole, a big hole, and we set off chemical explosions at different depths. And the goal is just to see how these shear waves propagate from the source as they go out. You can see the initial wave kind of come through, and then you see the waves, the shear energy just bouncing around due to the structure of the ground there. And then phase 2, we moved to a more complicated geology, dry alluvium. The third phase is in the southern part of the test site. In 1993, there was a very shallow sequence of earthquakes that happened to be really well recorded. They provide the opportunity to do this really cool direct earthquake to explosion experiment. We'll put instruments in the exact same locations so that we can do a very direct comparison between the earthquake and explosion with waves going through the exact same paths, so that we can really get at the source mechanisms that's not affected by depth of the event, it's not affected by the path, it's just, hey, what's the difference between this source of an explosion and this source that's an earthquake? I always thought seismology was cool when I can apply it to something that's as important as, being able to help keep our country safe, help keep the world safe. That's pretty exciting.
The main focus of the work that we do here at Livermore within the GMP, that's the Geophysical Monitoring Program, consists in using the lab's high-performance computing to simulate ground motions for large earthquakes in an area of interest. A big focus that our group has been the San Francisco Bay Area. We know the earthquake hazard is really high here, so we want to understand how ground motions affect different areas of the bay and use this to help us improve the seismic hazard assessment for the infrastructure of the bay. So to help us understand ground motions within a specific area, our group has used our expertise in the development and the use of very complex models that we can use to understand how a rupture happens on a specific fault. For example, here in the Bay Area, we have the Hayward Fault and can have a big high hazard. The video that we're showing here can actually show us a lot of specifics of where these ground motions will be higher. We can see from our simulations that the ground motions are definitely higher along the fault, and this is specifically for the Hayward Fault. But we can also see that certain parts of the bay can be more affected and have a higher hazard. For example, the San Pablo Bay, the Livermore Valley where the lab is, and the Santa Clara Valley. There we can see the ground motions concentrate there, so we know they're more vulnerable areas, and it's important information to give to the engineers so that they can address this in their modeling as well. Within the Geophysical Monitoring Program, we have one of the lead scientists in earthquake research, and to be able to couple that with the computing resources at the lab, it makes it one of the best places to do this. If you don't have those resources, you cannot push the science to the next level.